Thank you very much. Our next speaker is Theis from Mabyduck, and his talk is on realism-distortion trade-offs with people.
Thank you. All right, yes, so this talk is going to be about realism-distortion trade-offs. I know a lot of you are working on perceptual metrics, and you might find some of this content provocative. So first, I'm going to review what are realism-distortion trade-offs. And then I'm going to ask, can we measure these trade-offs with people from human feedback? And we'll switch gears a little bit and talk about the challenge of image compression, which is a image and video compression challenge that we've been organizing for many years, which might be interesting to some of you on its own right. And then we're going to apply realism distortion trade-offs to the click submissions, to the images that were submitted to this challenge. Just to set the stage a little bit, here's an image that has been compressed with a neural compression method. It's a very powerful method, but it has been trained for risk control, and this is a very low bit rate, so unsurprisingly we're getting some blur here. Of course, nowadays we have much more powerful methods, and we can generate very realistic reconstructions. So here we simply applied a diffusion model to this blurry image to synthesize the fine details. And then you get a reconstruction which is actually very hard to tell that it has been compressed at all. At the same time, of course, the distortion is actually increased for this image. So if we measure the PSNR will have dropped. And that's not really surprising to anyone. And most people would argue this is because PSNR is such a poor measure of how people perceive differences in images. And while that is true, there's actually also a more fundamental reason why the distortion drops, which is that this is essentially true or you can observe a similar effect for essentially any distortion. So even if you had the perfect perceptual distortion, you would be able to observe a similar effect where the more realistic image has higher distortion, and that's what I'm going to try to convince you of, and then we're going to measure these more perceptual distortions and this perceptual realism. Okay, so the realism distortion trade-off is also known as the perception distortion trade-off, which you may have heard of. So this was introduced by Jokai Blau and Thomas Michaeli in 2018. And basically what they've, let's see. Yeah, so what they've observed empirically first is if you try to measure realism, and for now it doesn't really matter so much how we're going to measure it, and you measure, some distortion, somewhat confusingly, higher realism appears lower on the plot. So just remember that lower means better, right? So all the good stuff is happening in the lower left corner, the bad stuff is happening in the top right corner. If you measure realism distortion empirically, what they found is that often you get only a bunch of methods which have relatively high distortion but high realism, good realism, or you get a bunch of methods which have low realism and low distortion, but it's very hard to achieve both. And this is for a bunch of super resolution methods in this case. And so there seems to be this region which is sort of unattainable, unachievable. And they measured this for a bunch of different distortions, and they always found sort of this similar pattern. But more important than the empirical results is they're actually able to prove that for a certain definition of realism, which is still quite general, you can actually prove that you have this kind of Pareto front, that you have this necessary trade-off between realism and any distortion. And here, distortion really can be anything. It could be, your favorite perceptual metric. If you also measure realism in this way, you will have this effect where if you increase the realism, your distortion will necessarily have to increase. And perhaps even less intuitive, if you decrease that distortion, you will have to sacrifice some realism if you're on that Pareto front. Of course, if we're somewhere here, right, we can increase both. But as soon as we hit that Pareto front, you sort of have to make that trade-off. Right, and so distortion is very general. The way that we measure it, we take some input image or some input whatever, and some output, and we just apply some function to it. That can be really anything, and then we take the expectation of that. That is our distortion. And perhaps a little bit more controversial, but we're going to get into this, why this is a good definition. The definition of realism that we're using here is a divergence. So here we're not looking at individual images, but we're looking at the distribution of inputs, and we're just looking at the distribution of outputs, and we're measuring the distance between those distributions. So once again, we're not looking at individual images and comparing them to individual images here, but we're really looking at that whole distribution of images, and we're comparing it to this whole distribution of outputs. This concept of a divergence is also pretty general. There's like one more technical constraint that they have, which I'm not going to get into, but mainly it's just saying, this is a function which is, non-negative, and it can be zero, or it has to be zero only when those distributions are the same, right? And so at least one thing that it already has going for it is if the divergence is zero, then we must have perfect realism, right? If those two distributions are really the same, your outputs are coming from the same distribution, and I give you an output, there's no way that you're going to be able to tell that this image has been compressed or in some way corrupted, because it looks exactly like a sample from the distribution of inputs. So you can't tell inputs and outputs apart. So in that sense, it's like a very, it's a sufficient constraint, right? So if I have that, I have perfect realism. No matter what else your definition of realism might be, if that is true, if your definition is reasonable, it will have to agree that those images are perfectly realistic. There's a more, maybe somewhat more intuitive definition of or characterization of divergences, which is that it's the performance of some optimal classifier for some loss, and I'm going to give you an example in a little bit. So actually here, so one of my favorite divergences is the total variation distance, and you can characterize it as the accuracy of an optimal classifier, right? So I give you an input or an output, you don't know which, and I ask you, is it an input or is it an output? And if you were able to measure the accuracy of the optimal classifier, then that gives you essentially the total variation distance up to some normalization, right? So if the images are perfectly realistic, the best classifier would have to guess, right? So the accuracy would be 1/2. So 4 times 1/2 minus 2 is 0, so the divergence would be 0 in that case. The question that we asked ourselves is, can we measure these kind of realism trade-offs, realism distortion trade-offs with from human feedback? Can we also observe that, for example, when we run some kind of subjective test? Can we observe that trade-off in human feedback? So far, like people observe that a lot in when they use objective metrics, right? So for example, FID versus PSNR. It's very easy to show these kinds of trade-offs, but I haven't seen anyone try to show this in any sort of metrics that were measured from human feedback. So that's what we're trying to do. And we're going to rely on this sort of characterization of divergences to design a kind of, not really a subjective test, but I guess a human study to do that. Again, we're kind of interested in the performance of a classifier, and so what we're doing is we simply treat humans as classifiers. We show them, for example, an image and ask them, has this image been, is this real or fake, or is this image, compressed or uncompressed, right? Some variation of that question. I think we actually asked, is this image raw or processed for the data that I'm going to show you? And so this study is also more fun for our participants, right? So they get this like little ding when they get the answer correct, and some other sound when they get the answer wrong, and so they also learn as the study goes on. And I think that's also like an important, important property here, because if you think about no reference metrics, they don't adapt, right? So they don't actually learn as you show them more and more data. Once the no reference metrics has been defined, maybe it has been learned from some data, but then it's fixed, and you apply it to this image and the next image and the next image, and it will always give you sort of the same response, whereas humans would learn in this study, and the same way this optimal classifier would adapt to the data that you're showing in a study. So in that sense, maybe this kind of classification way of thinking about realism is a more, I guess, a more appropriate way of characterizing what humans are doing. And to sort of measure something like a distortion, we're using these kinds of experiments where people can flick between two images and the reference, and we ask them which one's more similar to the reference, right? So they get image A, image B, and we ask them which one is more similar to the reference, and they can flick between them to really encourage them to compare the image to the reference. And then we're measuring what's called ELO scores. They're now like very popular in these like AI leaderboards, so you probably have seen them. But just in case, ELO scores are essentially just fitting a very simple Bradley-Terry type model to these pairwise responses. And then the ELO score tells you how good is one of these methods compared to another method. The difference tells you like what's the probability of picking one method over the other method. And then for the data that we're using the images from the Click24 challenge, which are 32 images, and we compressed them with two very powerful methods. So these are like very beefy neural compression methods. One is a transform coding approach that's using GANs for the synthesis. And one is a completely different approach that's based on BMVA. So that's a kind of, instead of transform coding, it's using something called reverse channel coding, but doesn't really matter. It's just important that it's like quite a different method, but they're both able to produce relatively realistic images at very low bit rates. And we're using the latest version of BMVA that was published by Jeremy von der Vecht last year, who also collected most of the data for this experiment. Right, so what does that give us if we now plot, this kind of distortion? These are square codes here because it's not really like technically a metric or a distortion, but some variation of a distortion. And here we're measuring realism with this kind of detection rate experiment where we're asking people to detect generated images. If we just compared one method against the reference, right? So we have like real images and we have generated images, and we put them into one experiment, and the method performs really poorly. What we would expect is 100% detection rate, right? Because you're always able to detect those compressed images. And if the images are perfectly realistic, we would expect 50% detection rate because people can't tell references from compressed images. There's a slight caveat here, which is that we didn't do this study where we only had one method against the reference, but we actually combined all of the methods and all of the bit rates in one experiment. And the net effect of that is that the detection rate might be slightly lower than 50%. It's not too important why that is. I'm just mentioning it so that you're not confused if you're seeing detection rates below 40%. That is the reason why. Right, so this is what we're getting if we just look at MSILM, this GAN-based approach, and we're looking at different bit rates. As you would expect, the distortion is increasing and the realism is getting worse as you decrease the bit rate. And now if we compare that to DiffC, we observe that DiffC actually has higher realism but worse distortion. So already here we can tell, and this is true for a number of bit rates, and at some point the distortion of MSILM just gets worse than diff C, so we no longer have this sort of trade-off. Then in that case, you would just pick diff C. But for higher bit rates, you would have to make a choice, right? Do I care more about realism, in which case I pick diff C, or do I care more about distortion, in which case I would pick MSILM? So that already shows that there is kind of like, it makes sense to think about these two quantities separately and maybe measure them separately. Okay, so next I would like to apply this to the data that we collected for Clique. And I'm going to briefly just tell you a bit about that challenge in case you're interested. So we've been organizing this challenge for now 7 or 8 years. And we just concluded the last iteration of that challenge in Aachen at the Picture Coding Symposium. Before I was also hosted at CVPR and DCC, but this year it was hosted at the Picture Coding Symposium for the first time. And it always has an image track and a video compression track. For us, for this talk, more important is the image track. There's always a validation phase and a test phase, and a validation set and a test set of 32 images. And we have 3 different target bit rates, a low rate, medium, and a high bit rate. And we've always been using this kind of like paired comparison with a reference and measured ELO score for evaluation. Till, who's also here, has been collecting the data for this. And the way we do this, we run this challenge is during the validation phase, people upload their decoder and encoded images to our server, where we decode them and then evaluate them. And then during the test phase, people are only allowed to upload encoded images. And we use the already uploaded decoder. And we release a new test set, so there's no sort of bias or possibility of cheating. And then we evaluate we do another evaluation of the test images. That's like a slight difference to the study that I showed you before, which is that people don't flick between the reference and the 2 images, but the reference is shown to the side, which, slightly different. One experiment that I thought was quite neat was something that we could do this year, because the validation set of 25 was the same as the test set of the previous year. One thing that we could do is we could compare Click 25 to Click 24 submissions, because we had methods evaluated on the same or submitted for the same set of images. And what we did observe this year is that we actually did not see a improvement in performance as measured by these ELO scores. And if we look at all of the submissions, so in blue of 25 and the first 2 submissions of 24, we find that most methods fall between the first and the second submission. So there might be like some kind of, so one reason could be that we're approaching some kind of rate distortion limit. Another reason could be that this year we encourage participants to be more computationally efficient. So we actually removed the 25% slowest methods. So people were encouraged to submit faster methods. And we do see some more evidence of that in our data. So for example, Kulchik, which is a very computationally efficient compression method, that significantly improved. So between 24 and 25, it got a lot better, even though the computational complexity is still extremely slow. It's just still extremely low. So it seems that nowadays people focus more on the computational efficiency in neural compression instead of trying to push the perceptual quality even more. Right. Guess, how much more time do I have? Like 1 or 2 minutes? It's all right.
I think you've got something in 20 minutes.
Okay, I don't think I have that much more to say, but yeah, perfect. Right, so yeah, so now we apply those two studies that we had before to this clique data. Again, on the x-axis we have our kind of distortion measured as the negative ELO, and realism on the y-axis. And what we observe is that, as a sort of general trend in this data, there's much more of a much stronger correlation between realism and distortion, which is perhaps not too surprising also if you look at the submissions, because they are quite similar. They're all these like GAN-based transform coding approaches. And for example, there was not a single approach submitted that was based on diffusion models. But even here, we do see some small changes in the rankings, right? So for example, if we compare these two methods, our choices would have flipped, or these two methods, we would have made a different sort of ranking or choice between them. All right, so to summarize, what the theory suggests is that we should treat realism and distortion separately. And I think at least as a sort of conceptual framework, it's very, very useful to even if you don't actively measure realism, I think it's like a very useful thing to think about, right? So for example, when we compare our metrics, our distortions to Moss scores where there was no reference in the study, right? So we're essentially comparing something that tries to measure distortion with something that essentially measures realism, right? So we're like comparing apples and oranges a little bit. And maybe we can design a study to more directly target the distortion, or maybe we can try to measure realism with our objective functions. And I guess we showed that these realism distortion trade-offs can be observed when you carefully measure that with even in human observers. At the same time, if you look at, I guess, slightly more practical methods, you might not call these neural compression methods practical, but from where I stand, they're more practical. Then realism and distortion are highly correlated, and maybe that's why people don't think so much about it now, right? Like they don't make this distinction so much as they should, maybe. But I think that's also going to change as we move towards more generative compression methods, right? Like maybe if you throw in a diffusion model like we did in the beginning, then you do start to see stronger differences between realism and distortion. And I think that's it from my side.
Thank you, Lucas. So, other questions? You want to handle the question part?
Hi, thank you very much. I just have a quick question regarding your data set. First of all, I really like the idea of showing correct and wrong answers to the users. But just a random one. Was it actually controlled on what type of device, what type of displays were they using when looking at the data set? And also another one, was it always shown in the same order to everyone, or was it random so they could? Did you spot any learning throughout the data set?
Yeah, so maybe first about so this was a crowdsourced study, so there's some limits to what we can do in terms of controlling the screens. We do some pre-screening where we check are they able to detect certain differences? Does the monitor have high contrast sensitivity, able to tell colors apart? Are participants able to do basic tasks basically? And even though the pre-screening is quite basic, or seems like a lot of people should pass it, we find that not many people actually do pass it. So it's quite a strong filter already. But of course, there's limits to what we can control. So there's a lot of things that we didn't control. For the learning, so we didn't try to look at the learning effect. What we do is we have a training phase where they see a couple of examples, and then those examples are ignored from the final analysis. Yeah.
Thank you.
Yeah, thanks for a very nice talk. I like this separation of realism and distortion. But if you were to add error bars to your plots, are you getting to the point that we cannot measure the differences between two compression methods because people also vary in opinions and maybe the what's the smallest delta that actually constitutes appreciable difference in either realism or distortion.
Yeah, so there's actually, if you look very closely, there are some error bars around these ELO scores that we measured here. There's like a faded region, and so we did collect a ton of data, especially for Click 25. We had to collect a lot of data in order to compute that ranking, because the methods were so close, and for 24 it was much easier to do this ranking, to do this evaluation, because methods were pretty far apart. They were kind of like nicely spread out. And this year everyone sort of submitted almost the same method, and it was very challenging to like find those differences. So yeah, we're getting to a point where, at least for Click, it's very challenging. But I think that partly is because the methods that were submitted were so similar. I actually don't think this is sort of the ceiling. I think with diffusion methods you could push this more, but you might have to sacrifice computational costs, right? So it depends a bit on whether you constrain the computational cost or not, whether we've reached that ceiling or not. Does that answer your question? Maybe I misunderstood the...
Yes.
Yeah.
Hello, Lucas. I followed a lot of work from you, so thanks for your talk. So comparing the distributions between distorted images and reference image and natural images are still very popular idea in IQA these days. But in practice, I discovered that how to define the distribution of natural images is very difficult because, for example, if we extract the distribution based on a certain content of images, and it influences the final result completely. So do you have any advice on how to define the distribution of natural images, aside from the Gaussian distribution theory in practice?
Right. I guess there's two questions that pop into my mind. One is, so for example, FID is very popular, right? And there we make this Gaussian approximation, and it works reasonably well, but of course we could do maybe better. And to be honest, I don't know what that better metric should look like. It's not something I've been focused on recently. But I guess another question, maybe I don't know if you asked this, but this is a question that's also very interesting to me, is the set of images that you use to measure these distributions. So that might also have a big impact. So and maybe less so for compression, but like when you move to things like text-to-image generation, what kind of what is the set of images that define your distribution, that can have a massive impact on like even when you ask people, not even just objective metrics. If you ask people, are these methods real or images real or fake? How you choose those images that you're evaluating has a huge impact on the outcome, and I haven't figured that one out yet. No.
Yeah, because in practice, the distribution, constructed distribution, is highly influenced by the semantic content, semantics, high-level semantics, instead of the low-level quality relevant statistics. So I think it's still a very hard question.
Yeah, exactly. Yeah, I guess if you have like a very specific application in mind, or like maybe you run a company and you just see what are the prompts that your customers are using, right? What are the images that they are looking at? What are the photos that they're uploading? Then you probably can make a more informed choice there. But if you're a researcher and you're just trying to come up with something a bit more general, then I think it's very hard. I don't have a good answer there.
Thank you.
Can I ask a last question? In continuation of your very interesting question, how long have you been running those experiments? And if you notice a shift in the realism percentage, because now we are mostly trained on AI generated content, and I'm just wondering whether people are now more selective, understand realism has shifted, or they are more tricked.
Yeah, so we haven't unfortunately, we haven't run those long enough yet to really know. Yeah, but that's something that I'm also interested in. Yeah.
Sure. Thank you very much.